Hello, I am Atul Penninti of the Department of Electrical and Computer Engineering, Colorado State University. Today, I will be exploring about the research topic Network on-chip design and optimization for many-core computing. What is network on chip? Network on chip is an efficient packet-oriented communication structure presenting high flexibility, scalability, and parallelism for fulfilling the communication requirements of applications. NOC architectures are becoming the backbone of modern multi-core systems due to their superior scalability and adaptability compared to buses. They play a crucial role to ensure reliable and scalable connectivity between processing cores, memory modules, cache banks, and other input-output devices. The advancement and development of the energy-efficient system-on-chip designs motivated the research community to focus more on the development of the NOC-based designs to achieve high performance and low power consumption in the SoC architectures. In a multi-core environment with several applications executing in parallel, system performance is significantly impacted by the network memory latency, noise reduction, temperature coefficient maintenance, thermal reliability, energy efficiency, power reduction capabilities, fault tolerance, and hardware Trojan security issues. Therefore, we dive deep into the citation works of few of the most notable and elite researchers in the field of NOC architecture and design technology, thereby discovering several holistic and evolutionary algorithmic frameworks which are used to optimize and overcome such challenges. In the first paper, we propose a holistic framework that integrates novel scheduling techniques for both network and memory accesses and operates cohesively in an application-aware and memory-aware manner to optimize overall system performance. The proposed dual packet scheduling framework comprises of two components. An anti-starvation technique is proposed which decides the starved status of a packet depending on not only how long it has been delayed, but also depending on its destination. Secondly, an application and memory-aware packet classification with two stages is proposed, where in the first stage we dynamically measure the memory intensiveness of an application at runtime, and in the second stage we consider the memory level parallelism capabilities of an application to assign its final weights. Finally, as shown in slides 2.2 and 2.3, the experimental results indicate that our technique performs well for systems with high-speed memories, improving system throughput by up to 16.7% and memory latency by up to 11%, and also energy consumption by up to 10% compared to the state-of-the-art works on NOC packet scheduling. Our experimental evaluations also indicate that the proposed scheduling framework not only outperforms the traditional scheduling technique used in many multi-core systems, but also improves upon some of the best performing recent works in the area of packet scheduling. In paper 2, we propose to employ the inference model in order to build an NOC modeling framework that is simple enough and yet that offers meaningful ways to track the spatially and temporally correlated behaviors of a network. As an application test bench, we use this framework to design a design methodology for dynamic voltage and frequency scaling. Whenever a new application is implemented by the NOC-based system, the main steps are to initially reset the specialized inference model and then evolve it for a specified time interval given by the adaptive stopping strategy. Later, the model evolution is led to a network islanding that represents the basis for VFI partitioning. To build a specialized influence model, one can place traffic monitors on each of the physical channels of the NOC and use their reading to compute probabilities. Intuitively, the probabilities should be a proportional measure of the amount of traffic between two adjacent routers. Finally, the influence model has further ramifications in other application domains as well, including multicasting in ad hoc networks, self-application for autonomous vehicles, and distributed decision-making. In paper 3, we propose an evolutionary algorithmic framework to synthesize hybrid photonic NOCs by utilizing particle swarm optimization and simulated annealing algorithms. The basic idea of the PSO algorithm is to mimic the social collective behavior found in nature and utilizing it to solve complex problems. As the flits are moved from the source to destination in an NOC, the PSO process can select among various values such as the number of WDM channels or PRI size. The simulated annealing algorithm is usually an evolutionary algorithm that generates solutions to optimize problems using techniques inspired by annealing in solids. Through the experimental analysis, we can derive that both the algorithms successfully increase WDM degrees as core-to-core communication increases, whereas PSO provides higher number of uplinks compared to SAE as the amount of global communication increases. The PSO synthesis approach optimizes the hybrid NOC fabric, achieving up to 18 times the power reduction compared to the traditional electrical NOC, demonstrating significant promise towards generating low-power communication fabrics that meet the performance objectives. One of the most challenging problems in CMP design today is the design of the on-chip communication fabric that interconnects the multiple cores on a chip. The on-chip communication fabric is responsible for satisfying strict latency and bandwidth constraints that are relentlessly increasing in stringency as application performance approaches the peta and exaflop levels. So, in this paper, we propose a UC-photon, a novel hybrid photonic NOC communication architecture which is optimized to cope with the variable bandwidth and latency constraints of the multiple. The UC-photon communication architecture comprises of the 3D integration with separate planes for logic and silicon photonics. For the 5 multiple use case applications explored in this work, UC-photon shows up to 46 times the reduction in power dissipation and up to 170 times reduction in energy delay product compared to traditional electrical NOC fabrics, highlighting the benefits of using the novel communication fabric. In emerging 3D NOC-based chip multiprocessors, aging in circuits due to bias temperature instability stress is expected to cause gate delay degradation that, if left unchecked, can lead to untimely failure. In this paper, we propose a novel runtime framework, Artemis, for intelligent dynamic application mapping and voltage scaling to simultaneously manage aging in circuits and the PDN and enhance the performance and lifetime of 3D NOC-based CMPs. Aging-aware application mapping and DVS, which is responsible for mapping L applications which arrive at an epoch, and circuit and PDN aging analysis. And emerging 3D NOC-based chip multiprocessors aging in circuits due to bias temperature instability, stress is expected to cause gate delay degradation that, if left unchecked, can lead to untimely failure. Therefore, in this paper, we propose a novel runtime framework, Artemis, for intelligent dynamic application mapping and voltage scaling to simultaneously manage aging in circuits and the PDN and enhance the performance lifetime of 3D NOC-based CMPs. Here, two techniques are discussed, where the aging-aware application mapping and DVS is the inner loop, and circuit and PDN aging analysis is acting as the outer loop. Our methodology to evaluate system aging and the result maximum attainable performance accounts for progressive effects of IR drops due to PDN aging, VT degradation due to circuit aging, and the temperature profiles over the chip lifetime. The experimental results indicate that the Artemis enables the execution of 25% more applications over the chip lifetime compared to the state-of-the-art works. Ultimately, an aging-enabled routing algorithm that balances the degree of aging between NOC routers and cores is derived, thereby increasing the combined lifetime of both. NOC architecture design faces a trade-off between various conflicting metrics. In this paper, we target one aspect of the trade-off, which is area versus average delay. According to application requirements and design constraints, The application process could be controlled by the designer and by specifying weight factors for area and delay. Therefore, as a proof of a concept, GA-based technique is applied to three real applications with different number of cores. Our GA-based technique runs to find the best architecture with respect to both area and average delay. Each generation consists of 10 different chromosomes representing 10 different architectures. 4 new architectures are generated by the crossover, and 4 remaining architectures in each generation are produced by random mutation, as shown in the figures. In Paper 7, the main goal of the work is to exploit approximation techniques intelligently to minimize the energy consumed by the NOC in moving data between NCs and the cores without slowing down the application in many core GPU platforms. An overlay circuit assigned to an MC lasts for a time duration determined at runtime, and the reply plane NOC is equipped with a global overlay controller that decides time duration for which an overlay circuit is established, and modified bypass routers which flits traverse in X or Y axes in a single cycle stopping at a turn. Experimental results show that Dapper reduces the energy consumed in GPU by up to 50% with up to 99% application output accuracy and minimum performance overheads. Paper 8 addresses the impact of nanometer layout on the design of NOC and shows the necessity to consider interconnect parasitic effects in early stages of design, even when no physical layout is available. With optimal repeater insertion, the growth of the interconnect delay becomes linear with a violent. However, for large high-performance designs, the number of such repeaters can be prohibitively high and can take up to significant fraction of active silicon and routing area, and additionally can consume significant amount of power. Also, global interconnects with and without repeater insertion are considered in this research. In Paper 9, we have developed and proposed a unified simulation framework named as ECE-561 for the simulation and analysis of the important parameters such as latency, throughput, energy, and power of the NOC system. This framework is mainly an enhanced and updated version of the well-known simulator ECE-561, which an additional performance parameters and integration of different NOC components and simulation platforms. An external mapping is also developed to evaluate the mapping results of the existing NOC simulation platforms. Paper 10 is an extension to the research work done in Paper 3. The aim of this paper is to explore the PSO algorithm to find optimal solution for shortest paths. To enhance the efficiency of routing algorithm, PSO is optimized. Also, a multi-NOC design with PSO algorithms for various subnets is integrated to avoid overcrowding, power gating, and packet scheduling policy. By using this method, the performance improvement at varying network utilization is achieved. It preserves extra energy which is developed at long duration in grid system. In Paper 11, we propose a novel runtime framework to reduce the power supply noise in cores and routers at runtime. The application profiling collects statistics on switching activity, power consumption, and NOC communication characteristics for all of the tasks of an application at different voltages and DOPs. The output of the framework is the task to core mapping, voltage assignment, and DOP selection for each application that allows for execution on the NOC-based CMP with independent power domains. The experimental results for the 7 nanometer FinFET process nodes show that our framework not only achieves up to 4.5 times reduction in PSM and up to 34.3% improvement in application performance, but also manages to map up to 38% more applications when the CMP is oversubscribed. Paper 12 proposes a novel runtime framework called Spectra to overcome temperature-induced reliability issues in PNOCs. The framework consists of a device-level reactive MR assignment mechanism that dynamically assigns a group of MRs to reliably modulate and receive data in a waveguide based on a chip thermal profile. Secondly, a system-level proactive thread migration technique is used to avoid on-chip thermal threshold violations, and reduce MR tuning trimming power by dynamically migrating threads between cores. Experimental results indicate that the spectra can satisfy on-chip thermal thresholds and maintain high NOC bandwidth while reducing total power by up to 61% and thermal tuning power by up to 71%. Paper 13 proposes an optimized buffer using an extended Hamming code to deal with MCUs and enhance the protected information storage, pursuing to reduce the area and power required for ECC implementation. As the technology scales down, the probability of MCUs increases, making the ECC the most used technique to protect stored information against MCUs. The optimized buffer evaluation is guided by measuring the fault tolerance efficiency, buffer area, power overhead, and performance of the proposed techniques. The results show that the proposed techniques reduce the area and power overhead in buffers with ECC and allows a considerable fault tolerance against MCUs with a small performance impact. A hardware Trojan in a PNOC can manipulate the electrical driving circuit of its MRs to cause the MRs to snoop data from the neighboring wavelength channels in a shared photonic waveguide. This introduces a serious security threat. Therefore, in this paper, we go through a framework called Soteria that utilizes process variation-based authentication signatures along with the architecture-level enhancement to protect data in a PNOC architecture from snooping attacks. Going further, PVAC and REAC enhancement schemes are deployed so as to protect the data from snooping attacks. Evaluation results indicate that our approach can significantly enhance the hardware security in DWDM-based PNOCs with minimal overheads of up to 10.6% in average latency and of up to 13.3% in energy delay product. In paper 15, we discussed the NOC exit strategies, where on analyzing simulation results made it obvious that an increased bandwidth between the network and connected resources would make the network perform better. But the price for this solution is that the packets now need to be buffered at the exits of the network. But from an overall perspective, the total buffers required is lowered for a moderately to a heavily loaded network. However, the network exit strategy hasn't received as much attention as the other parts of the network design is considered. Also, from the study through this research, no trade-offs involved in the increase of the network exit bandwidth are discovered. Ultimately, to conclude, all the above-mentioned holistic frameworks can be combined together upon carefully considering the pros and cons and be utilized to create a highly efficient and sheer-performing NOC design system. Also, I would like to thank respected Professor Sudeep Pasricha for providing me the opportunity to pursue this literature survey work by going through various works published by a few of the most notable and elite researchers in the field of NOC design and technology.